We had already set a record. To go back to 250,000 years continuously in the Arctic is more than twice as long as the Greenland ice sheet record in terms of a continuous climate history. So we could have stopped right there and already had an amazing climate story to share with the climate community and to learn about the Arctic. Lake Elgegikon is quite special in that it's located in a particular part of Russia that was not glaciated during any of the ice ages of the last few million years. It represents a part of western Beringia, in other words, the land bridge that linked Asia with North America. Lake Elgegikon was formed by a massive meteorite impact at 3.6 million years ago. We think that the impactor was perhaps maybe a kilometer across, and it produced a basin. The hills that you see around here literally outline the edge of the crater itself. There are 50 streams that come into the basin and then eventually into the lake that provide the sediment record. Over time, since 3.6 million years ago, all of the sediments, the pollen, the organic matter that's collected here has been shed into the lake. Also, the organisms living in the water column of the lake that are sensitive to temperature and chemistry of the lake have all been deposited at the bottom of the lake. So we have layer upon layer upon layer of information of what the climate of the surrounding watershed has been like since 3.6 million years.
Julie is a professor at University of Massachusetts Amherst in the Department of Geosciences. Her research expertise and important contributions are in Arctic marine and terrestrial paleoclimate records. She was the U.S. chief scientist of the Lake Elgegikon drilling program in northeast Russia. Julie has a BA in geology from Albion College. She has masters and PhDs from the University of Colorado Boulder. She had postdoctoral fellows at the University of Bergen in Norway and the University of Alberta in Edmonton. And she's been at UMass Amherst since 1987. Hopefully you will enjoy this presentation, but I want to mention that we are keen to let you know about this program, and we're very excited about the results that Julie has to report. We do indeed enjoy the ability to undertake this level of research when it's well reviewed and we can pull it all together. So, Julie, if you would come up.
Thank you very much for this opportunity to share with you some of the results from our scientific drilling of the Lake Elgegikon meteorite crater. The actual drilling was undertaken in 2009, and so I'm happy to report to you some of the really fascinating results that have come from this project. And for those of you who are familiar with climate studies of all sorts, in order to understand the climate of the Earth as a system, we need records from a lot of different locations on the planet. And so one of the motivations for going to northeast Russia, into a very remote location, in order to investigate what climate change record look like from this particular area, because if a hammer hits the climate system, we want to see what parts of the Earth respond to that hammer. On the other hand, if the climate system has a pinging noise, what other parts of the Arctic system operate or change? And so by understanding these records from different locations, we can learn a lot more about the climate system. And I want to acknowledge my other co-PIs on the screen, Martin Mellis from the University of Cologne, Pavel Manuk from the Nesri Institute in Magadan, and then a host of about 50 to 60 other scientists and graduate students who have been part of this work. Lake Elgegikon is a meteorite impact crater. The meteorite impact occurred 3.6 million years ago right on the Continental Divide in the Anadyr Mountains. And it created this crater you'll see here, 18 kilometers across. It contains a lake in it that's 12 kilometers in diameter. So if you remember the really bad movies, Armageddon, Deep Impact from many years ago, this is that kind of impact. I first learned about Lake Elgegikon in 1994 from Olga Glushkova. There was very little, if any, work had been done on this basin. She showed me a picture of this lake and talked to me about the potential that this lake could have a very long record. And I also want to highlight here these red stars are recently collected cores by the Ocean Drilling Program from the Bering Sea, with which we hope to, in the future, be able to connect a lot of the records that we have to look at a real Western Pacific notion of climate change. So here's a cross-section cartoon of the actual basin where we did our work. We first took a small borehole down to 142 meters in the alluvial fan materials on the side of the crater here using a Russian drill rig. And then we used the DOSEC GLAD 800 or Global Lake Drilling Rig on the frozen surface of the lake here to collect a series of overlapping cores that go on down through the Pleistocene into the Pliocene record back to 3.6 million. And then we also collected 200 meters of impact rock, that's the red materials below, for a different group of scientists to study. So we were able to develop a composite record from these three cores. Now, the first challenge for most geologists is to establish a chronology for the cores. Geologists are like time lords, if you know Doctor Who. We can go backwards and forwards in time looking at climate change, and in this case we're going back 3.6 million years. But we need to set that chronology or know exactly where we are in time. So this host of wiggles, I only appreciate that you see wiggles. That's all you should see. The orange one is insolation at the high latitudes. And there's an organic proxy that we've measured in the lake here. The red one is the alternating paleomagnetic normal reverse time scale, which many of you might be familiar with. The purple one here is a global marine ocean stack, sometimes referred to as the Lasecki-Ramos stack. It represents a global proxy of climate change going from very warm conditions to the glacial interglacial change up through time over here. And then there's a number of other proxies here that we've measured through the cores. There are a number of new instruments available, XRF scanning instruments, color spectrometers, line scanners that allow us to produce very high resolution data on these cores. So using all of that information, we come up with this very simple curve. Here's the paleomagnetic time scale over here, and this is the depth in the core down to 318 meters. Across the top is age, and we have about 14 or 15 different paleomagnetic tie points, and then over 500 tie points that are linked to the global record. So we feel very confident about the chronology in this record. We actually have 7 tephras from Kamchatka. We're having some little difficulty with the chemistry in dating those. So with that chronology, let me just show you a little bit about what the sediments look like. Here in the lower right-hand corner, you see the different sediment facies in here, and they're absolutely stunning in terms of their preservation. And we also put large kudos out to the DOSEC Drilling Company, who did a fantastic job with collecting these sediments.
My name is Tim Martin, and I'm the Earth Science teacher at Greensboro Day School, which is a K-12 independent school in Greensboro, North Carolina. Polar Trek is funded by the National Science Foundation and is such a wonderful opportunity to get teachers that are in the classroom out into the field to have this real experience, to have their students follow them, ask them questions from halfway around the world. Had the opportunity to interview with Julie Brigham-Getty here at UMass, and she selected me as the teacher to accompany her on the Lake Elgagitkin expedition.
This is control central here of the project, and one of the things that we like to do as scientists in the field is try to take a look at the first initial data and make guesses and speculate about what we found so far. What we have here on the wall, if you just look across the wall here, are some of the first printouts of the one property that's being measured in the cores, and that's magnetic susceptibility. And we know from the magnetic susceptibility record that it gives us kind of an index of climate change in a rough way, that the magnetic properties of the sediments themselves are telling us something about warm periods and cold periods. They don't tell us how warm or how cold, but because of the intensity or particularly the concentration of magnetite, it tells us something about some of the processes going in the lakes.
So given the wonderful preservation here, what I'd like to do now is step through some of the major highlights that we're learning about. And one of the most astounding things about this record is, in fact, that we're seeing intervals in the Arctic back through the last few million years that are much, much warmer than anyone expected. And that's really the bottom line for today. So up here you see a curve that goes from 0, the present on the left, and up to 3.6 million on the right. And I want to highlight the most recent part of the record here, back to about 600,000 years ago. So if we click on that, and what you see here, again, at top, this one, the same color coding. This is insulation. This is the marine stack. And then these two lower curves are a ratio of silica to titanium. We can look at productivity in the lake by measuring the silica of the diatoms. And then we can look at the clastic input, how much sediment was coming in, and use that ratio as an index of climate change. And then this lower one here that we see in red is our color index. So let's look at this particular interval we call marine isotope stat interval 11. So this is at about 410,000 years ago. Now, first of all, I want to say that if we go over here to this number 5 here, this is about 120, 130,000 years ago. To this point, no one had much of any terrestrial record anywhere in the Arctic older than this. So everything you see here in this diagram from stage 5 on is absolutely new. No one's ever seen this before in the Arctic in a continuous record from the land. We know from looking at this stage 5 here, 125,000 years ago, the Arctic was a little warmer than now. Globally, we were 1 or 2 degrees warmer than present. The Arctic may have been 2 or 3 or 4 degrees warmer than present. And scientists agree now that the Greenland ice sheet at that time was probably 40 to 50% of its present size. So we can see what the Arctic does in a warmer world. So let's look at stage 11 at 410,000 years ago. And again, this diagram, this is just the paleomagnetic stack. And if we take this little interval right here and expand it out, this goes from 450,000 to 380,000 years here. So we've blown up stage 11. Here's the insolation curve. And this is the record of climate from Vostok, from Antarctica, in this curve, in temperature. This is biogenic silica, or again, climate. Think of it, temperature of warm and cold, from Lake Baikal in Russia. And then 400 kilometers away, this is again, warming and cooling in Lake Elgegikin. And the amazing thing that astonished all of us was that, in fact, you could go to Antarctica, you could go to Lake Baikal, and you could go to the northeast part of Russia and see the exact same similar types of climate change. The same signal is happening in all 3 of these records. So this was not just a backwater lake in the middle of nowhere, but a lake that's actually recording a global signal.
One of the reasons that we take 2 adjacent boreholes is to actually make sure we get the complete sequence. As we're drilling down, there are, of course, core breaks, and we don't want to miss any material between core breaks. So if we take cores that are overlapping in this way, we can make sure that we have the record reproduced on both sides. And here's a perfect example here where we have a gap in the record where we lost recovery in this section, but in the adjacent borehole, we were actually able to capture that here. So you can see another gap in this portion of the record where we lost some of the material in the core, but we were actually to capture it here.
In terms of the vegetation around there, and on the left I have color-coded. The red here is just trees and shrubs. When there's lots of trees in the Arctic, you know it's got to be warm. And the cooler intervals here in blue. So this is, again, stage 11. This is the pollen, preservation of the pollen that records the vegetation at the time by Pat Anderson at the University of Washington and Tolya Loshkin in Magadan. Their pollen records then have been transferred into a biome model by Pavel Terezov, which allows us then to reconstruct paleotemperatures. And what this shows is that through the interval of stage 11, the climate was in fact 8 degrees warmer than present in summer. That's astounding. Nobody's ever seen this before. And the green line here is just today's July temperature running through here. So this was astounding that not only was it warm, it was warmer than 5e in that previous interglacial. This is not what we had expected. Let's look at another one here. This now is in the center of this long stack from 3.6 million down to the present. And here we're looking at an event at 1.1 million called marine isotope stage 31. Now, we highlighted this because we knew from the Andril record in Antarctica that during this time, this was the last well-documented time when the West Antarctic ice sheet had disappeared. So we wanted to say, well, what happened in the Arctic at the same time? What happened at the other polar region? So we went in and looked at that particularly warm interval. And here again is a similar diagram, the paleomagnetic stack, and take this tiny interval here and expand it out. We looked at the pollen again, looked at the biome data, and again we got summer temperatures that are in excess of 6 or 7 degrees warmer than present. Not quite as warm as stage 11, but certainly much warmer than present during this time. So what can we gather from stage 31? Why was it warmer? What was driving that? It's very difficult. Once we go beyond the epoch of ice cores, back beyond 800,000 years ago, we don't have a direct measure of CO2. So other scientists like Hanusha here at Lamont Doherty has produced a paper where she suggested in stage 31 that the partial pressure of carbon dioxide in the atmosphere may have been in the range of 300 to 325. There's some error bars on those estimates. So it's possible that the carbon dioxide of the atmosphere was warmer during this particular time. We would expect a normal interglacial level to be about 280 parts per mil. So this is a little warmer, a little higher than what we would expect. If we look at from the southern hemisphere to the equator to the northern hemisphere here, we can also see that due to the changes in the Earth's orbit, the orbit around the sun, the tilt of the Earth, and the season in which we're closest to the sun, those influence also the energy coming into the upper atmosphere. And we can see that, in fact, during this stage 31, that, in fact, we were getting about 50 watts per meter square greater input from the sun at that time. So we could see that there was a Milankovitch, so we say, or orbital forcing part to this. And it looks like, in fact, the carbon dioxide at this time, about 3 to 3.6 million years ago, was close to 400 parts per mil, which is basically what we just hit this year. So we've achieved that already in our own atmosphere in our modern world. What it means for us is that with a very small change in carbon dioxide, we can basically be driving the Earth system toward a forested Arctic, toward eliminating some of our major ice sheets. Now, one of the questions I often get is, well, if today's carbon dioxide is at 400 parts per mil, and it's because of human intervention, why was the atmosphere in the range of 360 to 400 parts per mil in the Pliocene? What's normal about that back then? What people need to understand is that from the time of the dinosaurs, back 65 million years ago, the Earth's carbon dioxide and greenhouse gases have been declining in steps and starts over time because we think what's called the rock weathering cycle, or the rock weathering thermostat, that as we uplifted the Himalayas and we built mountain ranges in different parts of the world, the weathering products of weathering feldspar and other silicate minerals actually consumes carbon dioxide. With mountain building, we're actually bringing down gradually over millions of years the level of the carbon dioxide. So we wanted to then say, well, how does that link with Antarctica here? So this is a diagram which just, again, here's this marine stack, and these little crisscrossing wiggles of reds and blues show you the insolation change from southern hemisphere to northern hemisphere. And often it's a little bit out of phase, obviously, because of the tilt of the Earth. And then these are other bumps related to the eccentricity of the Earth and the orbits, again, relating back to this orbital forcing. So this line here comes right down through 31. And what we determined was that, in fact, when the West Antarctic ice sheet disappeared in stage 31, half a precession cycle later, the Arctic was super warm. So there was a direct relationship between those two. So for the first time, we saw a really nice link between what Andril had discovered just recently and what our project was looking at over the same periods of time. So it's really very fortunate that we had the Antarctic Andril record to compare with to really place this in a global context. Thanks to NSF for both of those. So if we look at the West Antarctic ice sheet record, and these cartoons are wonderfully tell it all, that when the West Antarctic ice sheet in the Antarctica is expanded, this is a site that gets glacial tills. And the ice sheet here is shown in these models by Rob DeCanto. And then when the ice sheet retracts, or when the West Antarctic ice sheet is gone, like you see in this diagram here, you get diatomaceous ooze. In other words, the oceans are open, and there's productivity, and the organisms that are thriving there can then fall to the seafloor and create these diatomaceous oozes. So when there's diatomaceous ooze, there's no West Antarctic ice sheet, and a debated size in the East Antarctic ice sheet. So let's look at what that means for us. Here's isotope stage 31 in the Antarctic record, no West Antarctic ice sheet, this little yellow blip right in through here that I just mentioned to you. But I want you to notice that, look, there's several places here going back, and there's this M2 interval is at 3.2 million, when there are other times when the West Antarctic ice sheet disappeared. Now, this was amazing accomplishment for Anduril to be able to demonstrate that the West Antarctic ice sheet was not a stable phenomenon, that in fact it is vulnerable and able to come and go. Let me bring that back to Lake Elgegikon now. This diagram is simply our proxy going back from 0 to 2.8 million. And if we zero in on this one, this is stage 31, stage 11, the last interglacial here, and the Holocene, the last 10,000 years. Comparing these 4 different warm periods, what I want to bring your attention to is this diagram shows changes in vegetation, but down here is a biome reconstruction of the July temperature for these 4 different interglacials, and we're living in this one right now. And then this is also mean annual precipitation. And what I want mainly to see here is that both isotope stage 31 and 11 were much warmer and much wetter than anything we've seen in the Arctic before. This is an absolutely unprecedented record. We didn't expect it, and it certainly was a big surprise for us to see this, but it certainly seems to be holding up really well.
These numbers really need to be tested by additional work by chemists who are working on reconstructing PCO2. So it's really just a start to understand that. But we know that once we get to about 800,000 years ago, in the ice cores in Antarctica, we do know what the carbon dioxide measurements were. And given that we know that, many of these warm interglacials still need an explanation because we don't have high CO2, but we have very warm Arctic conditions. So what it tells us is we have a lot more to learn about the feedbacks in the Earth system between the ocean and the atmosphere, and then the role that the Arctic plays in that. And we don't have answers for all of those questions right now, but that's where we're going with the research.
And understanding what a proxy is, where, you know, it would be nice if we had a temperature record going back into the Earth's history. We don't have that. So we have to ask the environment what it was like. And so we look for microfossils, and sometimes we might not be able to say the water temperature or the air temperature was specifically a certain temperature, whether it's 70 degrees or 50 degrees. We don't know that exactly because we don't have that thermometer back in time. But if we find small fossils of animals that liked warm water or find other indicators of cold water, we can understand what the climate was like. And like I said, my students can become the scientists understanding the Earth's history.
Now Yulia is dropping the pipe down the hole. We're going to measure the depth of the ice.
And it's really great when they realize their environment around them today is recording the history of what's going on right now. And that will be recorded in history for the future.
Now we lift up the tape.
So what does this mean? If you take that record and think about it, here is, of course, during the last interglacial, what the Greenland ice sheet may have looked like. And if you look over here to stage 11 and stage 31, maybe this is what Greenland looked like. So what it means is that Greenland is not only just this ice sheet that sits there no matter what the North Atlantic does. In fact, probably comes and goes and has come and gone much more frequently than any of us had imagined. Now, stage 11 and 31 are not isolated. There are other, what we're calling super interglacials in the Lake Elgegikon record. And they have a number of different proxies that all point in the same direction, and particularly they're extremely well laminated, as you see here. So let me just show you what we've summarized from that. This top diagram are the sediment facies in the lake from 0 to 2.8 million. And the red areas, here's stage 11, stage 31, and you notice 49, 55, 77, 87. There's many other warm super interglacials when it was very warm in the high latitudes.
Now, to put this in perspective, most of the records that we have from the Arctic on land only go back about 125 to 130,000 years ago, even in lake sediments. So for us to push back and go into many serious interglacial cycles all the way back to 3.6 million, but even through the Pleistocene to 2.6 million, it really shed light on the fact that the Arctic was actually much more susceptible during warm periods to having a major makeover. And what I mean is that several of these interglacials allowed the tree line to advance all the way to the Arctic Ocean, and so completely eliminating tundra, perhaps. At least for this region, we were quite surprised to find that these interglacials were as warm as they were. One of our big questions is what drove that warmth? What were the forcing factors? And those are the kinds of things that we're working on.
So with that, I want to end by summarizing, first of all, that the Elgagikkan record is offering us a glimpse for the very first time in one location. Lots of surprises. The first of all being that we have extreme warmth many, many times throughout the last few million years. And this extreme warmth has major implications probably for the stability of the Greenland ice sheet and also for the sea ice history of the Arctic. That in fact, it may be much easier to get rid of that sea ice than we thought before. And the other important point that has emerged from this is that we can see the forcing and the interplay between the two polar regions in both the Andril record and the Lake Elgagikkan record in a new way. And so that by comparing these two records now with lower latitude marine records, we're really going to learn a lot of new things and have new questions to ask about the climate system. And with that, thank you very much.
Thank you, Julie. Any questions or comments from the board?
Maybe you said this. The carbon dioxide is the same as during that, I think it was the M31 period. Is there a boreal forest around the...
So in stage 31 at 1.1 million, yes, we see dark coniferous forests come back to the lake.
But is it there now?
No.
Because the carbon dioxide is the same, you said, right?
No, but let's say it's coming. I mean, if you look at all across the north, tree line is marching north. The shrub tundra is starting to move into the open tundra regions. So, I think even though we're at approaching 400 parts per mil now, the Earth system has to catch up. Richard Alley has said this before, that, hey, Greenland is still thinking decades ago. Greenland hasn't even caught up to where we are now. And so the transition to actually see the vegetation move will take many, many decades.
Any other questions or comments? I was wondering, just from the technical point of view, the Andril drilling versus the drilling that you were doing, have there been any technical swaps in terms of the ability to do the drilling and recover cores that, were developed in Antarctica and adapted in the Arctic or reverse?
Yeah, and there might be people here who can correct me if I say this wrong, but some of the tools that were down at the end of the drill pipe in the Andril project were actually developed in part by DOSEC. So they shared that technology and know-how. So we had DOSEC helping us with the tools on that end. But also in the design of the drill rig, which had to withstand very cold temperatures, we had to basically pull it out of boxes and pulled it out of 16 shipping containers, and pull it together at minus 40 degrees, and then be able to have it insulated well enough so that we could work inside there under no matter what conditions. We tapped Alex Pine, who had worked from New Zealand, who had worked on the Andril rig, to help us understand how to design the actual rig itself for the extreme conditions. So there was a lot of back and forth. Many, many years ago, even during Cape Roberts, I remember a conversation with Scott Borg saying, can I use your Cape Roberts drill rig in the Arctic someday? So we were able to actually build our own system to pull that off.
Thank you. Any other questions or comments? Thank you, Julie, for
Again, thank you for the opportunity.
presentation.